Hello, this is Richard Hammack's Calculus 1 course. We are in part 4 of the course on applications of derivatives. Today, lecture 31, local extrema and the first derivative test. Everything we do today hinges on what we did in the previous lecture 30, and I'll remind you of that here. The big topic there was increase-decrease of a function f. And we found that f increases where its derivative f prime is positive, and it decreases where its derivative f prime is negative. So in this picture, where f is increasing, its slopes are positive, so its derivative f prime is positive. And where f is decreasing, its slopes are negative, so f prime is negative there. Today we're going to be concerned with the special places where the derivative changes sign, either from positive to negative or negative to positive. The places where the function f stops increasing and starts decreasing, or stops decreasing and starts increasing. And those special places, those points on the graph, here, here, and here, that are the tops of the hills of the graph or the bottoms of the valleys, those are called local extrema. Let's start there. We're going to make a big definition here. Suppose C is a number in the domain of f. We say that the value f of c is a local maximum of f if f of c is greater than f of x for all x that are nearby c. So here's the picture. Look at this point c and think about f of c, which is this y value way up here. If you take a value of x that's close to c, like right here, f of x is going to be a little bit less than f of c. So for this point c right here, f of c is greater than f of x for the x that are close to c. And so we call this y value, f of c, a local maximum. And likewise, there's another local maximum of our function right here at this number c. F of c is greater than f of x for values of x that are nearby c. So we would call this f of c a local maximum. The word local means we're only looking at points nearby c. This local maximum is actually lower than the local maximum over here, but we're only concerned with values of x that are close to c, so it doesn't bother us that there are points higher than this maximum on the graph. So the thing about a local maximum is, as I said, you can look at it as the top of a hill in the graph. Points on either side are lower. And another way of saying that is that at the point c, the x value of c, as you read from left to right, the function f stops increasing and starts decreasing. So right here at this local maximum, before we got to it, we were increasing, we got to it, and now we're decreasing. At this local maximum, reading from left to right, we were increasing, and then we switched to decreasing. There's a companion definition. We say that f of c is a local minimum of f if f of c is less than f of x for all x that are near c. So a picture of a local minimum would be right here at this value of c. If you look at f of c, it's that y value. If you took an x that's nearby c, f of x is a little greater than f of c. So f of c is less than f of x for x that are near c. You could think of a local minimum as the bottom of a valley in your graph. Points on either side of that are higher. Equivalently, at C, the function f stops decreasing and starts increasing at a local minimum. You stopped decreasing and you started increasing at C. So these are big definitions. They'll be with us for most of part 4 of the course and beyond. A few vocabulary words here. A local maximum or a local minimum is called a local extremum. So this is a local extremum, this f of c is a local extremum, and this f of c is a local extremum. For the plurals of these words, the plural of local maximum is local maxima. So we have 2 local maxima here. Plural of local minimum is local minima. And the plural of a local extremum is local extrema. So we have 3 local extrema in this picture. And I want to point out that a local extremum is technically a y value f of c. And it occurs, we say it occurs at the x value c. So at this value of x equals c, we have a local maximum of f of c. F of c is technically the local maximum. It's a y value. So we will be concerned with finding the local max and local min of functions in today's lecture. So when you think about doing that, one of the first questions you should ask is, where do these local extrema occur? There's a theorem that answers that question, and it's this. If f has a local extremum at x equals c, then either f prime of c equals 0 or f prime of c is not defined. And if you think about it, this theorem is very commonsensical and obvious, really. You can see it when you look at the graph of a function, like the one graphed here. Think about local extremum. Pick a place where there's a local extremum, and there's 2 possibilities. First of all, it could be that f prime of c is not defined. You've got a sharp corner or a cusp on the graph where there's no tangent line, so consequently f prime of c does not exist. It's not defined. So that's one possibility. On the other hand, think about a local extremum where the derivative is defined. What would f prime of c be? Well, at this local extremum right here, for example, f of x has stopped increasing and started decreasing. So it's neither increasing nor decreasing at c. So what could f prime of c be? Well, it couldn't be positive because that would mean f is increasing at this point. It couldn't be negative because then f would be decreasing. So the only possibility is that f prime of c is equal to 0. So in a nutshell, that's kind of a proof of this theorem. If f has a local extremum at x equals c, then either f prime of c equals 0 or f prime of c is not defined. So what's the takeaway from this theorem? It's that if we are looking for local extrema of a function, then we need to look no further than those points x equals c, those numbers x equals c, for which the derivative is 0 or undefined. Those points are so special and so important that we're actually going to give them a name. Here's the definition. They're called critical points. A critical point of a function f is a value x equals c in the domain of f for which either f prime of c equals 0 or f prime of c is undefined. So the 3 values of c that are shown here in this graph, those are critical points for the function f. Either the derivative at c equals 0 or it's undefined. It's important to note that the critical points, according to our theorem, are special in that if we've got a local maximum or a local minimum, it's going to occur at a critical point C. But conversely, if C is a critical point, then f of C, it may not be a local extremum. And you can see that here in this graph, like right about there, there's a number C for which f prime of C is equal to 0. This graph, which was increasing, leveled out to a slope of 0, but rather than starting to decrease after that, it continued increasing. So this C, because f prime of C is equal to 0, is a critical point of our function f. But there's no extremum there. So the important thing about critical points is they really narrow down the search for local extrema, but they only give the candidates for local extrema. You could have critical points that don't correspond to extrema, and others that do. Critical points are important for us because, as suggested by the theorem, they narrow down the search for local extrema. So we'll be very concerned with finding them. And here's how to do it. It should be pretty clear how to do it from the definition of a critical point. First of all, you've got to find the derivative because C is going to be a critical point if the derivative is 0 or undefined. So the first step is to compute the derivative. Then you want to look at the values for C, look for the values C for which f prime of C is undefined. Just identify them, and that's your second step. And that's as simple as looking at the expression for the derivative that you get, analyzing it, and deciding what values of x can't be plugged into it. Do they give division by 0 or so on? Finally, you want to find the number C for which the derivative is equal to 0. So for that, you have to set up an equation, f prime of x equals 0, and you've got some algebraic expression for f prime here, and solve it. Find the values of x that make that derivative 0, and each solution is a critical point. So we're going to be finding critical points a lot today, but we're not going to do an example of finding them right now. There's one more topic that we need to address, and then we'll start looking at examples. And that topic is the highlight of today's lecture. It's called the first derivative test. And it is a means of finding all of the local extrema of a function f. And it goes like this. It's really intuitively obvious. There's really nothing to prove here. Here's what it says. First derivative test. And the purpose of this is to find all local extrema of a function. It states that the following. Suppose C is a critical point of our function f, like here, 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 or there. First of all, if the derivative f prime goes from positive to negative at C, as you read from left to right, then f of x has a local maximum of f of C at C. So here, for example, the derivative goes from positive to negative, and we have a local maximum. Why? Because the function f went from increasing to decreasing. At C, it stopped increasing and started decreasing, and that's a local maximum. Likewise, right here, f prime changed from positive to negative, so f stopped increasing and started decreasing, and that's a local maximum right there at C. Secondly, if the derivative f prime of x goes from negative to positive at C, then f of x has a local minimum of f of c at c. Here we went from negative to positive as we read from left to right. That means the graph stopped decreasing and started increasing, and that's a local minimum. And finally, there's one more possibility. If f prime does not change sign at c, then there's just simply no extremum at c. And that happened right here. At this critical point c, f prime was positive on one side of it. It was equal to 0 at c, and it was positive after that. And that just means there's no local extremum. So that's the first derivative test. Note that the first derivative test is all about answering a question about a function f. Where do its local extrema occur? It uses the derivative as a tool for answering that question. So ultimately, it's asking something about f. It's answering something about the function f. Where are the extrema? So let's put this all together. We now have a procedure to find all local extrema of a function f. The first thing we'd want to do is find all the critical points of f. The values of c where the derivative is 0 or undefined, because we know that's where extrema could occur. Second, apply the first derivative test to each critical point. Look at the change of sign. The first derivative test will tell you whether you have a local maximum or a local minimum, or neither. Let's look at an example where we carry out this procedure to find the local extrema of a function. Let's find the local extrema of f of x equals 2x cubed minus 3x squared plus 5. The first step in our solution, as we noted on the previous page, is to look for the critical points of f. And for those, you have to find the derivative, which is easy in this case. The derivative f prime of x is 6x squared minus 6x. So the critical points of f are going to be those values for which either the derivative is not defined or it's equal to 0. Looking at f prime, you can see that it's defined for all values of x. So you're not going to pick up any critical points here of the flavor where f prime of c is undefined. But you could have some for which f prime is equal to 0. And to find them, you have to take this derivative and set it equal to 0. And solve. Now, in solving an expression equal to 0, one way to do that is to factor the expression. So let's start there. We could factor a 6x out of here. So f prime is 6x times x minus 1. And we set that equal to 0. And you can just read off your solutions, x equals 0 and x equals 1. So the derivative f prime of x equals 0 if x is 0 or x is 1. So 0 and 1, therefore, are our critical points. So we've just carried out step 1 of our procedure. We've found the critical points. There are 2 of them, 0 and 1. We know that if we do have any extrema for this function, they are going to happen at these 2 critical points. So in step 2, we need to apply the first derivative test to these critical points. And that involves looking at whether the derivative changes sign on either side of these points. So draw yourself a number line and put those critical points on it. And then look at the sign of f prime. We've done this before. To figure out the sign of f prime, you could look at its factored version. It has 2 factors, a 6x and an x minus 1. Look at them individually. The 6x is positive when x is positive, so to the right of 0, and it's negative to the left of 0, where x is negative. Then look at the other factor, x minus 1. It's positive when x is bigger than 1 and negative when x is smaller than 1. So putting these together, their product is f prime of x on this rightmost interval. For any x, you have a positive times a positive, which is a positive. So we put positives there, telling us that f prime is positive on this interval. On the middle interval, f prime of any x in there is a positive times a negative, which is a negative. So we put negatives here to indicate that f prime is negative for these values of x. And then on the leftmost interval, for any x you pick, f prime of x is a negative times a positive negative, which is a positive. So looking at this, you can see that at x equals 0, f prime changes from positive to negative, and the first derivative test tells us we have a local maximum at x equals 0. So that's the first part of our answer. F has a local maximum at x equals 0. And remember, the local maximum is really a y value. So we should note here that that local maximum is f of 0. And if you plug 0 into f, you get 5. So good, we have a local maximum at x equals 0. But notice also we have a change of sign of the derivative at x equals 1. It changes from negative to positive. And the first derivative test tells us then that f has a local minimum right there at x equals 1. So let's record that down here. F has a local minimum at x equals 1. And remember that minimum is technically a y value. It would be f of 1, which is 2 times 1 cubed minus 3 times 1 squared plus 5, or 4. So the local minimum is f of 1 equals 4. So we've answered our question. We found all the extrema of our function f of x. There are only two of them, a maximum, a local maximum at 0, and a local minimum at 1. And remember, we can actually draw the graph of our function. We've got our answer here, but we could take this one step further by looking at the sign of the derivative that tells us that f is increasing here and then decreasing here and then increasing again. To get a rough sketch of our function f, it's increasing until 0, then it's decreasing until 1, and it's increasing after that. So the graph of f looks something like that. You've got a local maximum right here, as you can see, and a local minimum right there. Let's do another example. In this example, we want to find all the local extrema of the function f of x equals x times e to the x on the interval from negative infinity to infinity. That's all of the entire real line. Now let's carry out our procedure. The first step was to find the critical points. And the second step would be to apply the first derivative test. Let's carry out the first step. Find the critical points. Of course, that involves calculating the derivative. So let's see, here's f of x is x times e to the x. You got to use the product rule there. So f prime of x is 1 times e to the x plus x e to the x. You factor out an e to the x, that's e to the x times 1 plus x. That's your derivative. And we're looking for critical points, so we're going to set that equal to 0, and we're going to solve. Now, notice that e to the x, that's always positive no matter what x is. So the only way that this product could possibly be equal to 0 is if the 1 plus x were 0. And for that to happen, x would have to be negative 1. So we only get one critical point. It's x equals minus 1. Okay, so we've got our critical point. Now we're going to use the first derivative test. And remember, that involves plotting your critical point on the number line. So there it is, negative 1, right there. And then we've got to look at the sign of the derivative. Now the derivative, f prime, has two factors, e to the x and 1 plus x. I'm going to start off with e to the x, that factor all by itself. No matter what x is, e to the x is positive. So I've got positive straight across the board here. Now our other factor in the derivative is 1 plus x. Remember, f prime is e to the x times 1 plus x. Now as long as x is greater than minus 1, 1 plus x is going to be positive. But if x is less than minus 1, 1 plus x is going to be negative. So our derivative, f prime of x, which is the product of those two factors above, its signs look like this. On this first interval, before we get to negative 1, the derivative is a positive times a negative. So it's a negative. Negative's there. But on the interval after negative 1, f prime is a positive times a positive, so it's positive. And that gives us our answer. The only critical point was at negative 1, and the derivative changed from negative to positive there. So by the first derivative test, f of x has a local minimum at x equals 1 because of the negative to positive change. Had it been positive to negative, you would have had a local maximum, but it's changing from negative to positive, so that's a local minimum. And moreover, we have no local maximum, because if there had been a local maximum, you would have had a critical point somewhere where the derivative changed from positive to negative, and it just doesn't happen. And that's it. Now, before we leave this example, and I should point out that this answer is we answered the question that we set out to find all the local extrema of this function, and we found them. So before leaving this problem, I want to quickly draw you a graph of this function y equals f of x. You can get a pretty credible sketch of it. Let's see, e to the x is positive, so whenever x is negative, f of x is going to be a negative times a positive, so it's going to be negative below the x-axis for negative values of x. So it's decreasing here, and that's where the derivative is negative, and then it starts increasing. Right there at x equals 0, you have a 0 times e to the 0, you get a 0, and then after that, x times e to the x is positive, and you're increasing. So you'll see the graph changed from decreasing at that critical point back to increasing, reflecting the sign of the derivatives going from negative to positive, from decreasing to increasing f. Here's another example. We want to find all the local extrema of the function f of x equals the cube root of x squared minus 2/3 x. Again, on the interval from negative infinity to infinity. Well, our step 1 is to find the derivative. And if you're finding the derivative of this function, you probably you see the power rule happening. So the first step would be to convert your radical to a power. So let's do that. No derivative yet, but f of x is x to the 2/3 minus 2/3 x. That's just converting this radical to a power. And now we're all primed to take the derivative. F prime of x is, by the power rule, 2/3 x to the power of negative 1/3 minus 2/3. And let's simplify that. That power of negative 1/3 comes to the bottom as a x to the 1/3, which is cube root of x. So we get 2 over 3 cube root of x minus 2/3, and it looks like we could factor out a 2/3 from that. So there's our derivative, 2/3, 1 over cube root of x minus 1. Now we're looking for critical points, and remember, those are the values of x that make the derivative either undefined or equal to 0. What about undefined? Well, notice that if we tried to plug in an x equals 0, we'd be divided by a 0 right here, so f prime of 0 is undefined. And it's also noticed that 0 is in the domain of f. You can plug 0 into f, but you can't plug it into f prime because you'd be divided by 0. And that makes x equals 0 a critical point. But you could also get a critical point where the derivative is equal to 0. And this is pretty simple because if you just look at this factored form here, how could the derivative be equal to 0? Well, if this 1 over cube root of x minus 1 were 0, in other words, if 1 over cube root of x were 1, and that can only happen if x were equal to 1. So we get two critical points. We get critical points 0 and 1, because f prime of 0 is undefined, and f prime of 1 equals 0. Okay, now that we've got those critical points, let's set up our little number line over here with those critical points on it. And remember, we're going to look at the sign of the derivative f prime, whether it's positive or where it's negative, and that's going to give us our relative local extrema by the first derivative test. Okay, now previously we looked at these signs from factoring the derivative, and over here in this f prime there's not a whole lot to factor. In fact, what I'm going to do here is tell you about an alternate way to figure out the signs, plus or minus, of your f prime that you're going to put here. One thing that you can do is take what we call test points. Like, for instance, let's suppose you're looking at this first interval and trying to decide whether the derivative is positive or negative. One thing you could do is take a number that's in this first interval, just plug it into your derivative and see whether you get a positive or a negative, and that's going to tell you what the sign of the derivative is here. Let's do that. Now, you'd want to pick out a number that's easy to plug into your derivative. And notice in the derivative you're taking a cube root, so you want to plug in something where an x where you can take its cube root easily. How about x equals minus 1? That's in this first interval. And the cube root of minus 1 is equal to minus 1. So we should be able to compute that. So our test point is minus 1. And that's a test point in that first interval from negative infinity to 0. And we check f prime of minus 1. We plug minus 1 into the derivative. And here we're using this form of the derivative here. You plug in a minus 1 for x. And you work that out. And the cube root of minus 1 is minus 1, so this term is a minus 1 minus another 1, so that's a minus 2 there, times 2/3. You get a negative 4/3, and that's negative. So you plugged in a negative 1 to your derivative, and you got a negative, and that tells you your derivatives are negative in this first interval. Let's move to the second interval, from 0 to 1. We'd want to pick a test point in this second interval and plug it into the derivative and see whether we get positive or minus. But we want to pick a value of x in this first interval where it's easy to take its cube root, because that's what we got to do. Now, a number from 0 to 1, not including those endpoints, somewhere in this interval, on its interior, that's easy to plug into the derivative, easy to take the cube root. Well, how about 1/8? 1/8 is about right there. The cube root of 1/8 is 1/2. That's easy to work with. So that's going to be our test point in the next interval. The test point in the interval from 0 to 1, which is this interval, is going to be 1/8. So we do f prime of 1/8. That's 2/3, 1 over 3, cube root of 1/8 minus 1. And like I said, the cube root of 1/8 is 1/2. We reciprocate that. You get 2/3, 2 minus 1, and that's equal to 2/3, and it's positive. So we have positive derivative here in this second interval. Now, let's take one more test point in this last interval here for x greater than 1. That's the interval from 1 to infinity. You want to pick a value that's easy to take the cube root of in here. How about 8? The cube root of 8 is equal to 2, after all. So for our test point in the interval from 1 to infinity, it's 8. F prime of 8 is 2/3, 1 over cube root of 8 minus 1. And the cube root of 8 is 2. So that gives us 2/3, 1/2 minus 1. And that's negative 1/3. That's negative. And that's going to put negatives right here for your derivative. Okay, so we're at the point now where we can apply the first derivative test to see whether we have where we have a local max and a local max or a local min. Right here we change from negative to positive, and that gives us a local minimum at 0. And here we change the derivative changed from positive to negative, and that's going to give us a local maximum. So that's our answer. F of x has a local maximum at x equals 0, where we change from that should be, I'm sorry, typo. F of x has a local, I'm sorry. This is right. F of x is a local minimum at x equals 0. And here at x equals 0, the derivative changes from negative to positive. So the first derivative test says we get a local minimum. And that minimum would be f of 0, which if you plug 0 into f, you get 0. And f of x has a local maximum at x equals 1, where we change from positive to negative. And that maximum would be f of 1. If you plug 1 into f up here, f of 1 is 1/3. So that's our local maximum. So we're done. Before moving to the next slide, let me just quickly sketch a rough sketch of this graph of f of x. It decreases down to 0, x equals 0 there, then it starts increasing again, and then decreases again. So you clearly see you have a local minimum right here at x equals 0, where the derivative is undefined, and at x equals 1 you have a local maximum. No, you don't have to sketch that graph to get this answer. I'm just doing that to indicate what's happening to the function. New example. Here we're going to find all local extrema of f of x equals 1 over x squared, which is, as you know, x to the minus 2, again on the entire interval from negative infinity to infinity. So we know now that our procedure is going to be to find the critical points and then apply the first derivative test. So for the critical points, we have to compute the derivative. Here it is. F prime of x is negative 2 over x cubed. Now, that's not defined for x equals 0. So I put 0 down here, where the derivative is not defined, because you'd be dividing by 0. And here's f prime of x. It's negative 2 over x cubed, just bringing that down. And this is really easy because you can tell that when x is positive, the negative 2 over the positive number cubed, that's going to be a negative for positive x. And then if x is negative, the negative 1 over the negative cubed is going to be positive. So we have positives for the derivative. Now, watch out here, and let's not be on automatic pilot. You see the derivative changing from positive to negative at 0, and you want to jump to the conclusion that that means you have a local maximum at 0. That's what the first derivative test would say. But watch out, that's actually not the case here. And the reason is that 0 wasn't a critical point. And why not? Sure, the derivative f prime of 0 was undefined, but notice that f of 0 was not defined either. Try to plug in 0 to f, you divide by 0. That means 0 was not in the domain of the function f. Now remember, part of the definition of a critical point is it has to be a number that's in the domain of f, and this wasn't in the domain of f. So actually, the answer here is it has no local extrema at all, because 0 is not a critical point. If you graph this function y equals f of x, it's going to look something like this. There's no point on the graph at x equals 0, so you don't have a local maximum. So watch out for that kind of phenomena. Here, there's no extrema whatsoever for this function f of x. New example. Let's find all the local extrema of f of x equals x plus sine x on the interval from negative infinity to infinity. Well, we pretty much know how to do this now. We want to first of all find the critical points and then apply the first derivative test. To find the critical points, we have to compute the derivative. F prime of x equals 1 plus cosine x. There are no values of x that make that undefined, so we set it equal to 0. And so we have to solve, it looks like the equation 1 plus cosine x equals 0, which means cosine x equals minus 1. Now, looking at the unit circle, we have, let's see, the only place is here, x isn't plugged into cosine, so it's a radian measure. And the only radian measure on the unit circle that gives you cosine of that is -1 is cosine pi is -1. So, and then of course, so x equals pi is a solution to this equation. But then you could add multiples of 2 pi by taking laps around the unit circle. So the solutions of this equation, which are the critical points, are x equals pi plus k times 2 pi, or pi times 1 plus 2 pi. And here that k, remember that's an integer, it's 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. So you have pi times 1 plus 2 times an integer, and 1 plus 2 times an integer, that's just an odd number. So really, if you want to distill it down to its essence, those are all the odd multiples of pi. So the critical points are all the odd multiples of pi, like 1 pi, 3 pi, 5 pi, 7 pi, and so on. Let's draw them on a number line. So we next have to look at the sign of the derivative on these various intervals. And this is interesting. Here's f prime of x is 1 plus cosine x. Now, I put positives all the way across. Why? Because look at f prime, it's 1 plus cosine x. Could that ever be negative? Well, the smallest cosine of x could be would be -1, and in that case 1 plus that is equal to 0. Never will you have a value of cosine x that's less than -1 to make this 1 plus that value turn negative. So f prime of x is always positive except at these critical numbers where it's equal to 0. So never do we have a change from positive to negative, or negative to positive. So the answer here is no local extrema at all for this function. And that happens sometimes. Before moving on, let me show you a graph of this function. Remember the function is x plus sine of x. What does the graph look like in order that it has no extrema at all? It looks like this. Here's the graph of x plus sine x. Looks like kind of a wavy line. Now you'll see this dotted line right here, very lightly drawn. That's the graph of y equals x. Straight line, slope 1, y-intercept 0. That's the graph of just plain old x. And to that we're adding a sine of x, which is either means you're adding something greater than 1 or adding something less than 1. So the graph of x plus sine x looks like this wavy line like this that's always increasing. And notice that periodically it levels out, like right there it leveled out to a 0 slope, meaning that your pi right here was a critical number. F prime of pi is equal to 0. And then it kept rising. And you leveled out to 0 slope again at 3 pi. So 3 pi is a critical point of this graph. But was that a local maximum? No, it kept rising, and so on. So that's what the graph of this function looks like. And you can see from the graph why it has no extrema at all. It just keeps going up and up and up, almost like a stairway that's always going up. It levels out, but it goes up again. That's it for today. Let's close with a recap of the important topics from this lecture and the previous one. The takeaway is that if we want to understand the behavior of a function f, its derivative f prime can be used as a tool. A function f increases where its derivative is positive and decreases where the derivative is negative. The local maxima of f are the tops of the hills in its graph, and the local minima are the bottoms of its valleys. A critical point of f is a number x equals c in the domain of f, for which f prime of c is 0 or undefined. And we have the all-important first derivative test for finding local extrema. To determine what happens at a critical number c, look at the sign of the derivative. If it goes from positive to negative, f has a local maximum at c. If the derivative goes from negative to positive, then f has a local minimum at c. And if there's no sign change, then f has no local extremum at c. In our next lecture, we'll continue along this theme, but we'll look at what the second derivative says about the function f. It too can be used as a tool for understanding f, and it tells us important information about f. So next time, second derivative. I'll see you there. Goodbye.